Good morning, everyone. We're going to take some time to go through the practice problems from old GRs in preparation for the first GR this week. I hope by now everyone has had time to go through these practice problems on your own. If you haven't, please stop and go back and work through them before you watch this video. There are two reasons for doing that. One is we're going to go through everything kind of quickly, and it's important to make sure that you read these questions and understand what they're asking before we jump into the answers. Obviously, you're going to have to read questions and understand what they're asking this week. So, uh, yes, that is practice. You need to practice that. The other thing is, I want you to work through all of these questions and be sure you know what you're comfortable with and what you're less comfortable with before you see the answers so that you can study efficiently. Some of these are going to be very easy and straightforward. Others you're going to need to think about a little bit more. Everything looks easy if you're just watching me give you the answers. So please, by all means, make sure you work through them before you watch these. But here we go. Okay, so here are the old practice problems from old GRs. The first thing you're going to see when you open an exam is a formula sheet that looks like this, and I do want to point out, as I did last week, that everything here is here on purpose, nothing is here by accident. You should recognize the formula for the slope coefficient from OLS, and you should recognize the formula for the intercept from OLS. Those are easy. We've got a formula for a t-stat right here. There are only three things that go into this. The recipe for a t-stat involves the estimated slope coefficient straight from Stata or your favorite software, and then it involves the estimated standard error, which is also going to be straight from Stata or your favorite software right here. Okay, those two things you can just drag right out of the computer's output. The other piece here is going to be the null hypothesis coefficient, the value that you suppose the coefficient might be that you want to test it against. So you need to make sure that you know where that came from and know what value it's supposed to be in a given problem. Usually it's 0. By default in Stata, it's 0, but it doesn't have to be all the time, right? Now, we've also got down here the formula for a confidence interval. I hope everybody can make a confidence interval. The confidence interval for any statistic or a point prediction that you might give in a forecasting environment is usually going to be the same basic thing. You've got your prediction or your estimated statistic right here. And then to give this an upper bound and a lower bound, you'll take that statistic and you'll say, we're going to take that value plus or minus some number of standard errors. The nice rule of thumb is your estimate plus 2 standard errors is going to be the upper bound, and your estimate minus 2 standard errors is going to be the lower bound. But when we're being precise and we want a 95% confidence interval, you're going to need that critical value for a two-sided t-test that you're going to pull out of the t-table. What do you need to get the critical value for the t-stat? Alpha, the amount of how often you're willing to be wrong, such as 0.05 or 0.01 for 99% confidence. You're going to need that, and you're going to need the number of degrees of freedom, which you can find on this data output, which is going to be the number of observations in the data set minus the number of parameters you estimated in the model. Easy. We've also got over here the formula for the expected value of beta 1 in a simple regression when we've omitted a variable that should have been there. So here we're looking at a scenario where you should have two variables in the model and you only put one. Okay? And we can generalize that later to larger numbers. But the idea is, if I forget to put the second variable in the model, the expected value of the first coefficient is going to be the true value that it would have been plus something that has to do with the second variable. Specifically, we're looking at the effect of the second variable on our dependent variable, which is y, and we're looking at the relationship between the second variable and the first variable, the one we actually did put in the model. So those two pieces circled in red are very important. What else? Well, down here we've got the standard error for beta hat. Hopefully everyone remembers that there are only three things that can affect the standard error from OLS in a univariate regression, a simple regression. When there's only one variable on the right-hand side of the model, there are only three things that can affect the precision of the estimates. They are the size of the residuals, that is the error terms, the amount of variation in x, and the size of the sample, right? N minus 1. The only three things that can affect the precision of your estimates are, stop doing that eventually, are the amount of noise in the data, the amount of signal in the data, which is the variation in x, and the noise was the variation in the error terms. So you've got the amount of noise in the data, the amount of signal in the data, and how much data there is. Those are the only three things. When we step into the multiple regression environment, and we've got a second variable that we include in the equation, collinearity could happen, and that will also affect these standard errors. So the story with collinearity is if we have two variables on the right-hand side of the model, and they look a lot alike, it's going to be more difficult to estimate those coefficients because the two variables look the same. If they look very different, it will be easier. So what we have here is 1 over 1 minus square root of 1 minus the correlation squared. So this term here is actually the correlation of x1 and x2. Say core x1, x2. And it's squared, yes. And then you have 1 minus that thing, yes. And then you have the square root of that in the denominator. But what happens is when the correlation is larger, this whole term becomes large, and it makes the standard error large. When the correlation is smaller, this term becomes small, and it makes the standard error small. The best case scenario is when the correlation between the two variables on the right-hand side is exactly 0. In that case, this term on the right disappears entirely, and we're back to the nice story where there are only three things on the left-hand side that will determine the precision of those estimates. So make sure you're familiar with what those inputs are in this recipe, because those are the only things that are going to determine the efficiency of your OLS estimate. So very important things. Okay, first one. A researcher plans to study the effect of police on crime using data from a random sample of US counties. He plans to estimate the model crime is equal to, what do we have here? Beta 0 plus beta 1 police plus an error term. Okay, so crime is a function of how many police there are in an area. Crime is the county's crime rate, and police is the size of county's police force per capita. Okay, per capita makes sense, right? More police per person, per citizen, I should say. Good. The police commissioner asks whether per capita income is also important, noting that wealthier counties can afford a larger police force. Well, of course it is. The income in an area or the wealth in an area is going to be a primary determinant of both the size of the police force and the amount of crime that happens in that area. So, yes, absolutely. This is a very important omitted variable. Wealthier counties can afford larger police. Although, now notice this follow up, crime tends to concentrate in poor areas. Okay, so wealthier, more police, wealthier, less crime. Explain the direction of bias, if any, that you expect in the researcher's estimated beta 1 hat. Okay, when wealth is left out of the model, per capita income is omitted from the model. Use a relevant formula or concept to explain your reasoning. Now, here's what you could have done. You could have estimated a model like, say, for instance, beta 0 is equal to, let's make that smaller. That's a big fat coefficient. All right. You could have estimated something like crime. Sorry, Microsoft doesn't want to play today. Crime is equal to beta 0 plus beta 1 police plus beta 2 wealth. Now, in this case, it says per capita income, so you should say income, but I'm saying wealth because income or wealth, notice this, income or wealth would have the same kind of effect here. And there are other variables that you could probably come up with that would also be relevant omitted variables in this example. You're going to have to do that in one of these other problems here. So, and then let's plus epsilon I, an error term, right? Okay, you could have done that. And I know a few things. Explain the direction of bias, if any, that you expect in the researcher's estimate beta 1 hat. Well, I know that wealth lowers crime. Wealthier areas have less crime. So this beta 2 right there should be less than 0, should be negative. Isn't that right? And I know that the expected value of beta 1 hat from the other model, let's put this back together. The expected value of beta 1 hat, remember it's up here, right there. The bias in beta 1 hat is beta 2 plus this stuff on the right. Beta 2 covariance of x1, x2. So in this case, beta 2, this coefficient that I just wrote down, we agreed that that was less than 0. It's negative. The covariance of x1 and x2 is the covariance between, in this case, police and wealth. And we think that higher wealth areas are going to have more police. So this one is supposed to be greater than 0. It's supposed to be positive. First one is negative. So we've got something negative multiplied by something positive. So the entire red rectangle is negative, right? Less than 0. Bias. What can I say about the bias? Well, I could say that the bias, sorry, there's a plane overhead. This is locked for the record. It's supposed to be locked to the background. And Microsoft, did I not lock it to the background? I did. I know I did, because I was there when I did it. Well, now it's not even an option. The bias. What can I tell you about the bias? Well, the bias of beta 1 hat is equal to, it was beta 2 covariance of x1 x2 divided by variance of x2. Was it x2 or x1? Does it matter? It doesn't matter because they're both positive. See, it's x1. Variance of x1 doesn't matter because they're both positive. Variance of something. So beta 2 is negative. Covariance of x1 and x2 is the relationship between wealth and police, which I believe in this case is more wealth means more police. So this part is positive, greater than 0. This part is negative, less than 0. So bias is negative. Good. Based on your answer to part A, would the true effect of the size of the police force on crime most likely be more positive, more negative, or the same as the estimated effect in your model from part A? Well, the true effect, if the bias is negative, that means that the estimated effect is too low. That means that the true effect is higher than the estimated effect, right? The estimated effect is too low, I just said so. So the true effect is probably higher, would most likely be more positive. Don't we agree? Would most likely be higher right there. Good. Moving on with our lives. Problem two. A researcher would like to know whether higher earnings motivate injured workers to return to work more quickly. The idea is you're working, an injury happens at work, you have to take time off because of the injury. And the question is whether you go back to work more quickly or less quickly if you make a lot of money. As we said on Friday in class, there could be different things going on here. So the people who make a lot of money have a higher opportunity cost, right? When they're laid off, they're losing more money relative to what they could have made. But at the same time, the people who make a lot of money have a relatively low marginal utility of income. So if you're already a billionaire, do you need the money? Or would you rather just stay home? It's not obvious which way this is going to go, but we see this data, right? One observation for each worker variables: return, time until an injured worker returns to work in weeks, wage, weekly wages of worker I before the injury in dollars. The following output was generated for the model return. Okay. Fill in the blanks below to test whether workers with higher pre injury wages return to work in less time than workers with lower pre injury wages. What do I have? I want to test the null hypothesis that workers with high wages go to work faster. And because it says faster, it doesn't say differently. It specifically says faster, not slower. It's a one sided null hypothesis. Now, what I can do is I can say this wage coefficient, beta 1 hat, I can write my null hypothesis as beta 1 hat is equal to 0. And that's fine. I could also, though, because I know it's going to have a sign on it, I want to test whether they're less than 0. My alternative is going to be beta 1 hat is less than 0. So my null could be, let's go ahead and write that alternative. Alternative hypothesis, beta 1 hat is less than 0. My null could be that it is greater than or equal to 0. Great. Test statistic or p-value or confidence interval. Well, there's a t-stat, there's a p-value, there's a confidence interval straight out of Stata. But it does specify here the 1% level of significance. Notice that the confidence interval is 95% confident, so alpha is 0.05 instead of 1%. Can't use that confidence interval. I can use the t-stat, but I'd have to go look up critical values for these things. I can also use the p-value, which is clearly much less than 0.01. So I'm going to go for the p-value. That's the easiest. P-value 0.000. Conclusion and reason. Because this is 0.000, I am going to... Now, notice. That p-value is for one-sided or two-sided test. I made a mistake, didn't I? It's a two-sided p-value. So what am I going to have to do? I'm going to have to use this t-stat 9.74. Darn. Confidence interval was no good. The p-value was no good. I have to use the t-stat. Okay, fine. T-stat is equal to 9.74. What is my conclusion? Well, I need critical values for the t-stat. How many degrees of freedom do I have? 2, 5626, estimate two things, so 5,624. Oh my goodness, that's a lot of degrees of freedom. 5,000 degrees of freedom. So I'll go back up to here. I want to test this at the 1% level of significance. I want it to be one-tailed, so this column, 1% significance, one-tailed, degrees of freedom, 5,000. It sounds like my critical value should be 2.33. One-tailed, 1%, 5,000. Okay, 2.33. Critical value for T is 2.33. T crit equals 2.33. T crit equal to Re, re, reject. Good. There we go. Suppose we wish to test the null hypothesis that this thing is equal to 0.02 instead of the alternative that it's not equal to 0.02. So notice this one. This one is a null hypothesis that isn't zero, and the alternative is two-sided, okay? We've still got 99% confidence, so we're still looking at 1% significance. Alpha is 0.01. Which of the following pieces of information from state as output or are applicable for conducting the test? Mark all that apply. The t-stat. Well, the t-stat for stata has a null hypothesis that beta 1 is equal to 0. We just did this, right? So that one's no good, but it says mark all that apply. So I'm going to not mark it. And then the p-value. Okay, so this is a two-sided p-value, right? We almost made that mistake the first time. But this p-value is, again, for the null hypothesis that beta 1 is equal to 0 instead of 0.02. So this p-value is no good. But it says mark all that applies. So I won't mark it. What about the confidence interval? Well, Stata's confidence interval is always based on a 95% level of confidence, and we're asking for 99% confidence here. So that is also no good. None of them. You get full points by leaving this blank. It's the best possible type of question. Moving on with our lives. Circle the 3 words or phrases which best complete the following statement. Suppose you rejected the null hypothesis H naught beta 1 is equal to 0 in favor of the alternative that it's not 0 with 99% confidence. That means that if there had been a relationship or no relationship. Well, the way we interpret these, rejecting a null hypothesis means if the null hypothesis was true, we would only see a t-stat as large as we saw alpha of the time, alpha being something like 0.01. Yes, in this case it says 0.01. Okay, so if the null hypothesis was true, right? Because you have to write down something that you can reject. If the null hypothesis was true, beta 1 is 0, that means there's no relationship between these variables. Okay, so if there were no relationship between wage and return to work time, there's at most a alpha chance that we would have been wrong. So it's a 1% chance that the population parameter or test statistic, t-stat, would have been as extreme. Perfect. Perfect. Problem 3, the data set is the same as in problem 2. The newly added variable is age. Okay, the idea is if you're older, you probably don't heal as quickly from certain types of injuries. Maybe older people are going to be out of commission longer after a work-related injury. Yeah, the coefficient on age is actually positive here. So it does seem like that's true. And is it significant? Yeah, 2.81. That's fairly significant. Write a one-sentence layman's explanation of the estimated coefficient on wage using the numerical value in your sentence. Now, remember, wages here are weekly wages, right? Let's go back and check, make sure we get it right. Weekly wages of worker I before the injury, time until they return to work in weeks. So dollars per week, and then weeks off. Let's check this. Write an explanation for every, I'll say it, right? Or, yep, I'll say it because I know this thing is going to try to jump around if I try to write the whole sentence. For every dollar per week, we predict, for every dollar per week you make, we predict a 0.016 or 0.017, you can round that up, longer weeks off after injury. Point 0.017 weeks off longer after injury. Something like that would be valid, right? If I increase someone's weekly wages by $1, and they get injured, I expect them to be out of commission this much longer on average. Write a one sentence layman's explanation of the estimated intercept using the numerical value in your sentence. Well, if everything else is 0, wait a minute, what did I miss in part A? Right? You get this back and it says -5, lose 5 points. No, no, no. Don't forget, this is a multiple regression now, and so I have to say holding all else constant. Very important. Underline those. Write a one sentence layman's explanation of the estimated intercept using the numerical value in your sentence. The intercept here is just a constant. Okay, so it has a similar interpretation. We don't have to hold other things equal because we're actually going to hold other things equal to 0. If wage and age are 0, I expect this person to be off for 1.6 weeks on average. A worker with 0 wage and 0 age, which is obviously impossible, right? A worker with 0 wage and 0 age is off 1.6 weeks on average. Is off 1.6 weeks on average. Let's try it one more time. I have better luck if I try to do this very slowly. Good. Moving on to the next. Predict the time until a 50-year-old worker earning $1,600 per month returns to work after an injury. I have terrible news for you. $1,600 per month is not weekly wages. It's monthly. Okay, so you have to fudge this somehow. How many weeks are there in a month? 52 weeks in a year. Divide that by 12. Come up with the exact number of weeks in a month. Or suppose it's 4. For a question like that, that's a little bit unstructured, right? It's not really clear if you're supposed to say, okay, 52 weeks per year divide by. It's not exactly 52 weeks in a year either. So you get a little leeway converting this, but you do have to convert this. So suppose that this is approximately 400 per week. All right. So then we go back to the data. What do we have? We have this many dollars, $400 per week. Multiply that by this, and then they are how old? 50? You can do this. So we have 400 times 0.017 plus 50 years old, and each year older 0.07. Okay. 50 times 0.07 plus, and then what's the constant? 1.6? Yes, it's 1.6258 plus 1.6. And I want you to crunch that out and see what you get. That will be the time until a 50-year-old worker earning about $400 per week returns to work after an injury. Equals question mark. Of course, if you write a question mark on the exam, something bad will happen to you. Write a real number here. Do you think it would be very uncommon to see a 50-year-old worker earning $1,600 per month take 10 weeks longer than you predicted to return to work? So this worker, by the way, notice it says 50-year-old worker earning 1,600 per month. That's the same as this person, but it doesn't say anything about their actual wages. It just says, would it be unusual to see somebody 10 weeks longer than predicted? Would it be unusual to see somebody with an error term as large as 10? Well, how precise is this regression line anyway? I go back to the output from Stata and I say, look at R squared. R squared is low, right? There's a lot of variation in this data relative to the size of relative to the amount that we can actually explain with this model. But R squared is not the best way to answer this question. The best way to answer this question is the root mean squared error, which is the standard deviation of the residuals. And this says that on average, the predictions from this model are off by something like 22. Well, if on average you're off by something like 22, would it be uncommon to see somebody be 10 weeks off? No, I don't think it would be uncommon at all. I think it would be very common. No, RMSE is 22. So on average, we're off by 22. Uh, that makes 10 sound like a relatively good outcome, right? Suggest at least one potentially omitted variable which you would like to include in this model. My goodness, so many things, right? How about, well, what is it that, again, I point to R squared. Notice that the age and the wage of the worker tell you very little about how long they're going to be out of commission relative to the amount of variation in how long they're out of commission. So that means that there are other things that are way more informative, perhaps, or influential on how long it takes you to get better from an injury, a work injury. How about the type of injury? Doesn't it seem like that would have something to do with how long it takes for you to get back? I think it would. Type of injury should tell you just about everything there is to know, right? Type of injury. And then, for instance, the type of job you have is likely to be correlated with the type of injury. How much you like your job is likely to be correlated with how quickly you return to work. Some people don't like their jobs. Hate to tell you that. It's true. Um, Microsoft type of injury. Exclamation mark, exclamation mark, exclamation mark. Now, in a sample of 5,000 people, is it likely that we have a bunch of people with the same types of injuries? No, there are a lot of different ways you could hurt yourself. So even if we could categorize the type of injury, those categories are not going to measure exactly how severe the injury was for each person, but you can understand that fundamentally the quality of the injury is going to tell you a lot about how long it's going to take to recover from that injury. And so any information that can explain part of that is going to be very helpful. Using a relevant formula or concept, explain how your estimated coefficient on wage would change if you were to include your proposed variable into the model. Now here we go. Did I choose a good one? Now, the type of injury. How would your estimated coefficient on wage change based on including the type of injury? I'm going to go out and on a limb and speculate that people who make a lot of money working in an office in downtown Chicago or LA or Denver or New York don't have a lot of really severe injuries. Does that seem reasonable? People who work in the coal mines probably have more injuries. People who work with heavy equipment probably have more injuries. Factory workers probably have more injuries. So, type of injury. These severe injuries, even if our variable for type of injury, right? Because I didn't really say what that variable would be, but suppose it's severity of injury. The severe injuries are going to be correlated with low wage individuals, but the severe injuries are going to be correlated with a long time to return. Is that fair? I think it's true. So if the severe injuries are correlated with low wage, that means the correlation between the injury and the wage is negative. Okay. Severe injuries bias. Severe injuries increase return. Severe injuries decrease wage. That doesn't mean that they decrease your wage. That means that they're correlated with low wage jobs in this case, right? And then bias in beta 1 in beta 1 is equal to beta 2 covariance of x1, x2 over variance of x1. X1 in this case was wage, x2 in this case was um this severe, right, a severe injury or not. The severity of an injury. So more severe is a large x2 number and less severe is a small x2 number, something like that. Okay, so the severe injury increase your time to return. Beta 2 is positive, but a severe injuries are correlated with lower wage. It's positive. Covariance is negative, so the bias is negative. The estimated coefficient on wage is too small if we don't include the variable. So if we do include the variable, the bias, negative bias disappears. I think that wage coefficient might increase. This is wage coefficient. I say wage. Wage increase. How about beta 1 hat? Might increase if injury type included. That's my best guess. Moving on to problem 4. The first last estimator is an alternative to OLS for estimating the slope in a linear relationship. Now, the first last estimator is hilarious, but it's not necessarily a good estimator. Although the estimator is unbiased, you remember the simulation exercise from class. It was very funny. What else is necessarily true about the first last estimator? Assume Gauss-Markov conditions hold. Well, the first last estimator only uses the first observation and the last observation and draws a line between them. And in the case where x was a count variable and x just goes 1, 2, 3, 4, 5, 6, 7, 8, 9, it is unbiased. It's also consistent asymptotically. It's also surprisingly accurate in the simulation that we did in class. But because it only uses two observations instead of using the full sample efficiently, it is not efficient. What else is necessarily true about the first last estimator? It is inefficient. Why? If all the Gauss-Markov conditions hold, ordinary least squares is the best linear unbiased estimator. It's the most efficient estimator there is, period. So the first last estimator, as cute as it is, it will never do as well as OLS does. It's inefficient. Fill in the blanks. If you decrease the significance level for a t-test but do not change your sample, the probability of a type 1 error will blank, and the probability that you will fail to reject the null hypothesis, given that the null hypothesis is actually false, the alternative hypothesis is representative, would blank. Now, a type 1 error, the thing that happens most often, or the thing that is most obvious that can happen, is when we choose alpha. Alpha is how often we're willing to reject the null hypothesis if it is true, right? An alpha of 0.05 means I will only reject the null hypothesis 5% of the time when it's true. That's how often I'm willing to be wrong. An alpha of 0.01 means I will only reject the null hypothesis 1% of the time when it's true. That's how often I'm willing to be wrong. And that's a type 1 error. So if you decrease alpha, you will accidentally reject the null hypothesis less. You can imagine as alpha goes to 0, you will accidentally reject the null hypothesis less and less and less if it was true, right? So the probability of a type 1 error will go down. Is there any reason not to let alpha go to 0? Well, the probability of a type 1 error is going to go down, but the probability that you will fail to reject the null hypothesis, given that the null hypothesis is actually false. Okay, so if the null hypothesis isn't true, I want to reject it. And what's going to happen is if alpha is extreme, suppose alpha is 0.01 or 0.001 or 0.0001, some really, really huge number, which is to say tiny number, we'll start making the opposite mistake more often. Okay, we call that a type 2 error. You fail to reject the null hypothesis even though it is false. All right, alpha goes to 0. I am going to make a type 1 error less and less and less. It stands to reason that I will make the other type of error more. Decrease, increase. The standard error for a coefficient is, what is it? It's the standard deviation of the sampling distribution of that coefficient, which is the standard deviation of the coefficient estimates over repeated samples. If I could draw many, many samples from the same population and estimate the coefficient many times, that's the standard deviation of that set of estimates. I only actually get to do it once, but using the variance of y and the variance of x and the size of the sample, I can calculate exactly what that standard deviation would be, right? We saw the formula all the way back at the top. It's the standard deviation of the coefficient estimates of repeated samples. We saw the formula for that standard deviation all the way up at the top here, right? All you need to know is the amount of signal in the data, the amount of noise in the data, and the size of the data set. And if you could replicate that, the same amount of signal, the same amount of noise, and the same size data set, you could do that many, many times, and this is the standard deviation that you would get. And it seems reasonable that that's enough information to know what that standard deviation is. And then if you have correlation, of course, multicollinearity, we have a little bit of compensation going on for how that collinearity is going to affect the sample. Very good. Right, that's the end of the practice exam. Study hard and good luck.